Hi everyone, for those of you joining virtually, today's workshop is the sixth workshop in our beginner track series, and we'll be going over Numpy and Pandas, which are really useful Python libraries. The attendance code is Washington, D.C. for those of you that are diligently noting down your attendance every week. Okay, if you missed any of the links, feel free to ask Ben or Nikhil in the chat, and they can drop them for you. So there actually aren't many slides for today because we'll be working on a Collab notebook. So once you're on the slides, feel free to click on the Intro to Numpy and Pandas link here, and you'll be redirected to this notebook right here. So we'll just give you a few moments to get on here.
Wait, I don't see the link in the chat.
That's in the link. No moments.
Here's the link to the slides. Once you get on the slides, you should be able to access the link for the Collab notebook. Can I get a yes in the chat or some kind of affirmation in the chat once you're on here? Awesome, seeing some thumbs up. Is anyone not on yet? And feel free to say so, we can wait. I just want to make sure everyone can follow along today. All right, I'll take that as a good to go then. Okay, so if you're unfamiliar with Collab Notebooks, this is a really nice, oh, that should say yes in the chat. This is a really nice way for us to kind of work with Python and work with Numpy and Pandas. So if you want it, I highly encourage you to play around with this notebook. But if you're going to do so, please click on File and click Open in Playground mode. And this will allow you to make changes to the document without actually saving any of them. Or if you want, just make a copy of the notebook, and then you can do whatever you want with it. Just don't make any direct edits on here. Okay, we'll get started then. So what are Numpy and Pandas? As Nikhil mentioned last time, we're not actually referring to the animal panda when we're talking about pandas, in case you needed the clarification. Numpy is a linear algebra library for Python, and it's a really useful tool, and it really lessens our workload for a lot of the operations that you'll be conducting when you're working in Python, especially when you're trying to build machine learning models. And same thing goes with Python, and throughout this workshop, we'll just be exploring different functions that these libraries provide us with that allow us to conduct useful operations. Okay, so first off, we have to actually import this library, and we do that with a really simple statement saying import numpy as np and pandas as pd. The np and pd here are just standard protocol on what we sort of nickname these libraries. We could say import numpy as Bob and use Bob here wherever we used np instead. But it's just standard that we use np and pd. So go ahead and run that cell. You'll notice that if you try to run any of these other cells later on that refer to np without running this cell, you'll get an error. And that's because you have to make sure to import the library before you can access it. So one of the core tools that Numpy provides is the Numpy arrays are really useful ways of representing vectors or matrices. and you can conduct a lot of useful operations on them. So really quickly, has anyone worked with NumPy or Pandas before? Just let us know in the chat. Or also, like, if you're familiar with Python, we did do an Intro to Python workshop earlier this quarter. So if you're able to make it out to that one, that's great. That'll give you a really good boost for today's workshop. But even if you couldn't be there that day, or even if you're not familiar with Python, you should be able to follow along pretty well. Okay, awesome. We have some people in the chat that are familiar with NumPy. So I hope this is a good review in that case. But we'll get started. So here we're going to create a list, simple array, 1, 2, with 3 values. And Python treats this as a list object. Now, in NumPy, if you want to work with arrays, you can cast that as a NumPy array by just doing np.array and then passing in your list variable. And now you have an array here instead of a list. And later on, you can use this NumPy array for a lot of the functions you'll be performing. Quick note before I move forward, there's just a lot of different functions that we're going to be going over today, and in no way should you be trying to memorize them. This is just to kind of give you an introduction to familiarize yourself with. And in the future, it's just good to know that such functions exist that you can draw from when you're using the NumPy library. And you can always kind of look at NumPy documentation or even refer back to this notebook if you want a quick refresher. So don't try to memorize what we're going through, just try to play around and make sure you kind of get acquainted with how these work. Okay, so let's go ahead and create another list. This time it's a 2-dimensional array or a matrix. And again, you can convert that to a NumPy array by casting it as np.array and then passing in your another list argument. You can also create arrays and put in arbitrary values using some NumPy methods or functions. So one of them is np.arrange, and how that works is you provide np.arrange with an interval, and you also provide a step value. So here, if we run this, wait really quick, give me 1 second to collapse all these, or actually it's fine. So when we run this, you'll see that you get 3 values between 0 and 5 that are incremented by 2. Here, the lower value is inclusive and the upper value is not included. So between 0, 1, 2, 3, and 4, we get all the values that can be incremented by 2. At any point here, we're doing the same thing, except now we're incrementing by 50. And notice that 1,000 is not one of the values here because, again, 1,000 is not included in our interval when we use np.arrange. If you want to fill in your array with just zeros, we can use the np.zeros function and just specify how large we want the array to be. So np.zeros, as you can see right here, provides you with an array of size 5, all with zeros. And you can do the same thing with different dimensions as well. So if you want a 10 by 10 matrix that are all initialized to zeros, then you can use np.zeros here. It'll be kind of difficult to see right now where these functions will be useful, but next week when we're actually implementing linear regression, logistic regression, you'll see that we'll be using a lot of these functions. So for example, when we use np.zeros, we were talking about weight matrices earlier in our theory workshops. So initially when you don't know what your weight values are, you can just start off by initializing that matrix to be all zeros and then go from there. And we'll see how we actually use these later on, but just bear with us here and we'll just get through all of these. And just like zeros, you can also do that. NumPy also allows you to fill in ones for your vector or matrix. So again, we can do that with a 1-dimensional just vector or a 2-dimensional matrix. Now here's a different function that at first looks similar to np.arrange, but instead what we're doing here is we're specifying the size of your vector instead of the step size. So here again, you're looking at an interval, except this time the second value is included in the interval. So 0 is included in the range of values you can draw from, and 10 is also included. And you're just providing 5 evenly spaced values between 0 and 10. And we're doing the same thing here with a larger interval and more values. Between 0 and 100, here are 10 values that are evenly spaced. Any questions so far on how any of these methods work? All right, moving on. The np.i method essentially allows you to create an identity matrix. So np.i5 just results in a 5 by 5 matrix where the diagonal here is ones. If you've taken linear algebra or just from high school, you might be familiar with what an identity matrix is. But what's really cool about an identity matrix is if you multiply another vector or another matrix with the identity matrix, what's cool is that you get that same vector or matrix back. It doesn't alter the values in any way. So far we looked at how to generate values that are evenly spaced within an interval, but if you want to randomly generate values, and again, this is something that we could do when we want to initialize our weights, for example, to random values, we can use the random.rand method. So here we just generate 5 values between 0 and 1, and that's the default interval. So you can run this multiple times, and each time you run it, you will be getting different values that are all between 0 and 1. And you can do the same thing with higher dimensions as well. So here you have a 5 by 5 matrix instead of a vector. And again, every time you run this cell, you'll get different values because you're just randomizing them between values of 0 and 1. Now instead, if you want values over a standard normal distribution, and what this is referring to here is if you're familiar with the bell curve where the standard deviation is 1, this function here, which is really similar to random.rand, except there's a little in there that changes what values you're drawing from. Here you're instead drawing from a standard normal distribution, which again, a lot of the values you'll notice are between -1 and 1 or -2 and 2. And that's because if you look at a standard normal distribution, most of the values fall within that range of -2 and 2, and I think like 99% of all your values fall between -3 and 3. So that's why most times when you generate random values again, you'll notice that they fall within that range. And again, here, the argument you pass in specifies the number of values you want to generate. And just like with np.random.rand, you can do this with 2 dimensions as well. Now, if you want to specify an interval in which you're generating these values instead of just drawing from, a standard normal distribution, you can use the randint method for that. Right here, the first 2 arguments just specify the interval. So that's why we generated 4. If you run it again, you'll get a different value each time. But if you want to specify the size as well of random values you're generating, you can specify that in the 3rd argument. Now, can someone tell me how you do this if you want like a 2-dimensional array? Like let's say I want a 3 by 3 matrix of random values between 1 and 10. Any ideas on how you do that? And again, we're just experimenting here, so feel free to shoot out ideas.
For the 3rd argument, you'd probably put in like an ordered pair of like 3 by 3 or something.
Exactly, yeah. So this 3rd argument right here is reserved for the size. So you can specify the size within that argument slot, and you will get a 3 by 3 matrix. Can I get an estimate in the chat of the pace? Am I going too fast, too slow? Between a value of 1 to 5, 5 too fast, 1 is too slow. Can someone let me know in the chat how it's going? Okay, see a thumbs up, awesome. 3, okay. Beautiful, I'm seeing some 3s. Okay, we'll keep going at this pace then. So here are some more array attributes and methods. We actually already covered what both of these functions do. So does anyone want to unmute and explain what np without peeking in, scrolling up, what np.arrange is doing here and np.random.random is doing? Let's start with the first one. What does np.arrange do? So this is kind of tricky because earlier when we looked at np.arrange, we specified 3 arguments, I believe. Yes, we specified 3 arguments, but here we're only specifying 1 argument. So how this works is if you don't specify a lower bound for your interval, it's automatically assumed to be 1, or sorry, it's automatically assumed to be 0. And if you don't specify a step size, that's automatically assumed to be 1. But if you want, you could, specify the lower bound to be 2. Let me just run the cell and you'll see that here you're starting at 2 instead. But otherwise, if this isn't specified, the lower bound is just assumed to be 0. So I kind of answered the question because I realized we didn't go over the specific case. But for the second line of code here, can someone explain what it's doing? It is on the screen, but pretend you don't see it.
I think it would just generate 25, an array of 25 random integers from 0 to 100.
Yes, exactly. And you can already kind of see the output of the cell once you run it. But that's exactly what we get. You can count that this is 25 values, but just trust that it is because that's what we specified over here. Another really useful function is the reshape method. And exactly as the name suggests, you're reshaping your matrix to be a certain, or you're reshaping your NumPy array to be of a certain dimension. So here we have a vector of size 25 of 25 elements. So you can conveniently reshape that to be a 5 by 5 matrix. Does someone want to tell me what would happen if I changed this to, let's say, 5 by 4? You can try it out and let me know what happens, or just take a guess.
Some sort of error.
Exactly. And it makes, you would want NumPy to you would want Python to throw an error, right? Because if you just say, I'll just take the first 20 values because that's all I have space for, you're losing some data. So it's up to you to make sure that when you're using these reshape functions, that the shape is appropriate. But if for some reason it's not, you will get an error and you'll know something's wrong. These functions here are very self-explanatory, but we're going to go over them because they are useful. So again, we're looking at another array that we declared earlier. And these 4 functions, or we'll just start with the first one. So the dot max method just returns the maximum value within your array. But the argmax returns the index of the maximum value within your array. And notice that the index here isn't 2-dimensional. And that's because we actually didn't, we just printed out another array dot reshape, but we actually didn't assign that to another array. So another array is still actually, as you can see, it's still actually just a 1-dimensional vector. But if we instead assigned this back to another array, and if we run this cell again, you'd see that's two-dimensional. But that's why if you had the question, when we look at the position of the maximum value, we're still getting, we're not getting a two-dimensional index value. And then the same goes for the min and argmin. Min returns the actual minimum value within another array, and argmin returns the index. And if you're confused on why this is 12 and we have lower values here, that's just because this is from an old run thing. If we run it again, you'll see we'll get different values. And that's because for another array, we actually generated random values. So every time you do this, you will get different values. But there we go. This is right now where the minimum value is 4 and not 12 like it was earlier, I believe. Okay, let's look at the shape method. So earlier I said it's kind of up to you to make sure that, whatever operations you're performing, that the shapes and the dimensions kind of match and check out. But when you're dealing with really large matrices or NumPy arrays, it'll be kind of hard to kind of keep track of the shape. So shape is a really useful function where it, as the name suggests, it outputs the shape. So here, if we just did another array dot shape, we would just get 25 because it's one-dimensional. But because we're using the shape method on this entire, on this term right here, that's why we're getting a two-dimensional matrix. So we can reshape array. Notice that we're looking at array here, not another array. If this was another array, we'd again get an error because you can't reshape 25 values to be a 10 by 1 matrix. But you'll see that now, previously array was one-dimensional, but now it's two-dimensional. And again, when you run it, you'll see that the shape is exactly what we specified it to be, 10 times 1. The dtype method just returns the data type of values in the array. So you'll see that all of these are integers, as we would expect. Also, earlier when you're generating random values, you can specify the data type of the values you're generating. And if you want more information on that, you can just like search it up or look at Numpy documentation. But it just defaults to integer, which is why we get integer over here. Okay, moving on. If you're familiar with like list indexing in Python or just indexing in a lot of programming languages works this way, where you just specify the name of your array and then in brackets put the index value and you get the actual value located at that area. And again, indexing starts at 0. So if we look at array here, that's not the array. If we look at array over here, at index value 0, we have 0, and at 1, we have 1, which is why when we index into the index value of 1, we get the actual element 1. And then notice that when we do the same thing with reshaped array, we get 1, except it's returned in brackets, and that's because the reshaped array is pretty much the same thing as array, except it's two-dimensional. So you'll see that each of these elements within reshaped array is an array of itself, and which is why it's in brackets. Okay, let's look more into how we can index into arrays and slice certain portions out. So this is the same array that we were dealing with earlier. If you want to slice out certain values from or a portion of the array, you can just index through it like so. And you can also set a certain portion of an array to be a certain value. So here how this works is you go from 0 inclusive up till 5 not inclusive. So this would, as you can see here, this would access index values 0, 1, 2, 3, and 4. And just to kind of check that, We can do 2 instead here, and we get 2, 3, and 4 for what's changed to 10. Also, we'll see this later, is you don't actually have to specify this to be 0. If you just leave it blank, you start at the beginning and go up to, but not including index 5. But just for clarity, you can put that in there. And this is the same thing we saw earlier, except instead of specifying the last index value, we just kind of leave it blank, and it just assumes to go till the end of the array. So we start at index value 5 inclusive up till the very end, and that's exactly what you see right here. Can someone tell me what this is doing, where you don't specify any index values whatsoever?
It would take the start to be like as default to be 0 and the end to be the end of the array. So set everything to 20.
Exactly. And if you notice, slice only contains 5 elements, which is why we only see an array of size 5. And exactly, it just turns them all to 20, just like we saw with 10 here earlier. Any questions so far? Okay, in the next cell, we'll notice something really interesting. So here, when we changed these values to, sorry, one sec. Oh yeah, so here when we set all these values to 10, you'll notice that, our original arrays changed. So that's because we never actually made a copy of the array to change those values instead. So if you ever want to duplicate your array and make sure that you're not altering the original, you can use the .copy method, which does exactly what the name suggests. And now you can change array copy without actually modifying the original array. So here we're setting all values to 100. But then when you run array, you'll see that it's what we initially had. I know some of this might be a little slow or it might be self-explanatory, but it's just good to know these methods exist in the future when you realize that you need certain functionalities. Okay, indexing two-dimensional arrays. Can someone tell me what, I think we did already cover rent end. Can someone tell me what this line of code here does? Or more specifically, what each of these arguments stands for?
Yeah, the 0 is like the min of the rangey one, and then 100 is the max, and then it's asking for 16 different random integers from that range.
Yeah, perfect. So this is specifying the size of your array. And like we discussed earlier, you can make this, of different dimensions. It doesn't have to be one dimensional. You can put 3 by 3 here if you want. So we have some random values generated over here, and we can reshape them for the purposes of the demonstration of accessing 2D arrays or matrices. So to access, can someone tell me what this would output? And it's not 6 because this is from a past iteration of this piece of code. What would this line of code output? The first argument is the row index value, and the second one is the column index value. So if you just kind of take a look at our matrix that we have here. Ooh, let me check chat 1 second. 82. Yes, that is exactly right. Also, you could do brackets instead. This also works for indexing. Either's fine. So if you want to access certain, sections of the matrix, you can combine what we learned earlier to do some like cool operations. So here you're getting the first 3 rows. Again, this is the lower bound inclusive, upper bound is not inclusive. So you're getting rows 0, 1, and 2. And then here you're getting the columns starting at index 2 all the way till the end. So first 3 rows, last 2 columns, this section right here. Oh, yeah, this section right here. And then here we have the top left corner of the array. I'm just going to explain it one more time. And this is because, or actually, can someone explain why this notation right here gives us these 4 values? Just to kind of really hone it in. And someone that hasn't participated before. If you don't have to unmute, you can just say something in the chat. Okay, now we'll expand the audience pool to people that have participated before.
Yeah, so the empty colon, like on the left hand, means it's going to start from the beginning, and then it's going to go to this like second row, but not including it.
Mhm.
Oh, yeah, I think someone put it in. Yeah.
Yeah, exactly. Yeah, that's perfect. So the 2 isn't included. So you start from 0 because nothing's specified, like Austin was saying, and you just take the first 2 rows and the first 2 columns. Thank you for participating. Appreciate that. Okay, now let's take a look at some cool comparison operators you can perform on these NumPy arrays. So here's the array that we're working with. It was the same one that we generated earlier. If you want to, if you're not concerned with the actual values, but want to look at certain properties of your array, such as which of these values is greater than 50, you can get a matrix, except instead of integer values, you'll just get true or false values. This is greater than 50, this is not, and so on. And now you'll see if you use the function from earlier where you look at the data type, you won't be getting integer anymore because your data type has changed. And then here you're generating an array of the using the index value. So what this returns is all the index values, right? Where your elements are greater than 50. So now you're creating an array using just those index values, which results in this array over here. So if you were thinking of perhaps like implementing this in C++, you can maybe go through all the steps in your head. And this is why using a library is really useful, because it kind of shortens the work on your end, and you can just use simple operations like this and then get useful results. Thank you for sticking through so far. We are almost done with NumPy, and then we'll move on to Pandas. So let's look at some more array arithmetic. Most of this should be review, actually. So one more time, can someone tell us what this line of code does? We kind of reviewed this function earlier too.
It'll give you an array of single-dimensional array of 9 elements that are like random values from 0 to 10.
Yeah, perfect. And notice that it allows for repeat values as well. So for some reason, you specified your range to be like 0 to 5, but you asked for 9 elements. That's still acceptable because this function allows for values to be repeated. And then here we just reshape this to be a 3 by 3 array, which is why in the end we get a 3 by 3 matrix. Let's generate another array over here. And this is not reshaped, so it's still a single dimensional vector. So this is a simple matrix arithmetic that if you're familiar with, matrix arithmetic, this should make sense. But you can add two matrices together and it'll just be element-wise addition. So here we just added, each element with itself and you get this matrix over here. Same thing with multiplication. With this vector over here, we can multiply each value by itself and we get element-wise multiplication. So the 3 here becomes 9, 8, 64, and so forth. Okay, I hope you didn't see the line of code I just deleted, but if I did this, can someone tell me what would happen? Or actually, that should be fine. I'm going to change this to Y. Take a moment to look at our array Y and see what would happen if we did array Y divided by array Y. So actually forget that we're looking at array Y. Like in general, just looking at what happened here and here. What would happen if we use a division operator instead? Okay, so we got the right answer in the chat that with this specific array that we're dealing with, we would get an error since we're dividing by 0. If you see over here, we do have a 0 in our array Y array. But in general, this should work, theoretically the same as these other operators where you just do element-wise division. But you just have to be careful of this because in some cases, it might not work out. And that's why we have this nan value right here. It's because dividing 0 by 0 would throw an error. But doing this with x should be fine because our randomly generated array x didn't throw any errors. Yeah. So all of these are 1. Can someone take a guess as to what this line of code would do? If you're familiar with what the double asterisk stands for in Python.
You would probably just square all them.
Yeah. So the double asterisk in Python stands for the exponent operator to the power of exactly, someone said that in the chat. So you're just doing element-wise squaring of each of these values. There we go. Some other useful functions for element-wise operations, np.square root takes the square root of each of your array values. np.exp does e to the power of each of your element values. And you'll see that this is really useful too, because in some of our functions that we looked at, we had to you'll see that e and the natural log is something that we use very often in machine learning. So I think you'll, if you build machine learning models, you'll find yourself using this function a lot. For the element-wise there's a question in the chat. For the element-wise operators, the arrays need to be of the same dimensions, right? Oh, you mean right here? Yes, they do need to be the same dimension, is a short answer I'll give right now. But in a couple minutes, we're going to look at something called broadcasting, which is how NumPy deals with certain operations that you might perform where the dimensions don't exactly match. But for right now, for the sake of the next couple minutes, the answer is yes. But thank you for asking that. That's a really good question. Okay, and then np.sign, as you might guess, just takes the sign of each value in your array, and it treats it as radians. So if this value was 7, it would be sign of 7 radians. Okay, we saw in our theory workshops that there's a lot of linear algebra, matrix multiplication in machine learning. So knowing how to multiply matrices is a really useful tool. And you'll see that NumPy actually has, with NumPy, there's 3 ways that you can perform this operation. So here I just declared 2 matrices. So the first way that you can perform matrix multiplication is by using the np.dot method. And given just, given one-dimensional vectors, it just computes the dot product of C and D. And same thing with scalar. If instead C was just the value 5 and D was just the value 4, you would get 20 as your output. But if you were to pass in a matrix instead, np.dot, the method actually does matrix multiplication for you, and you'd get the resultant matrix. There's also the matmul method, which is exactly as the name suggests for matrix multiplication, except for with this, unlike with np.dot, multiplications of scalars is not allowed, so you would have to pass in vectors as your argument. But there's actually a much simpler way to conduct matrix multiplication with NumPy arrays, and that's just with the operator. And this operator is basically it's the same thing as what the star operator would be for scalars. So it's literally just stands for multiplication, except to kind of avoid confusion with matrix multiplication versus, just like scalar multiplication, this operator was introduced. So notice that, if we didn't cast this as a NumPy array, we would actually get an error. And that's because this operator is something that would only work with NumPy arrays. And there we go, we get the same answer. You'll notice that, like if you just need to do a simple matrix multiplication operation, this is probably the best way to go about it, just because it's just simpler and cleaner. Okay, the very last topic we'll discuss with NumPy is actually a very important topic, and that's broadcasting. Essentially, what that is how NumPy treats arrays of different dimensions. We got an excellent question in the chat earlier on whether these operations that we're performing on arrays has to be, of like dimensions that match. And there are some rules that these dimensions have to match, but we'll take a closer look at what those rules are right now. So here we declared an array we declared a vector of size 4 and a vector of size 3. Now, typically, if you were to just try to add A and B and then output it, you would get an error because the dimensions don't match. But there is something you can do to perform this operation in a certain way that you'd still be able to get, your desired output. And that's exactly what this piece of code right here is doing. So how this works is right now, both of these vectors are one-dimensional. But with broadcasting, if when you perform operations between 2 different arrays, either the dimensions have to match or one of the dimensions can be 1, and you can have an element-wise sort of operation conducted over each of these elements. That might have confused you a bit, but we'll actually take a closer look on this page right here. But we'll just look at this example for now. So here what we're doing is we're taking A, but then we're also adding a new dimension to it. So now the shape of A is, now A is 2-dimensional. So if we actually run this and you'll notice that A is now of dimensions 4 by 1 if you use the dot shape. And if we actually output C, you'll see that we don't get an error. And if you take a closer look at what happened, each of the elements of B was individually added to A, and we instead got a 4 by 3 matrix because we started with a 2-dimensional array instead of a 1-dimensional one. Okay, if that confused you, it would confuse me too, but we're going to take a closer look at exactly how this is working. So here are like the 2 core broadcasting rules that I was explaining earlier. Also, by the way, really quick, this is the Numpy documentation site, and we're looking at what their documentation says for broadcasting. But usually when you're working with any kind of library, you'll be able to find documentation online that tells you exactly how each method works and what each argument stands for. So if you're ever confused, this is a great resource when you're working with NumPy, just looking at what each part of the library does and how it works. So let's just take a couple more minutes to look at what broadcasting is. So here are the 2 general broadcasting rules, right? So either when you're conducting an operation between 2 arrays, either their dimensions have to match or the dimension can be 1. So here you'll see that, these dimensions match. You're multiplying this 3D array with the 1D array, but this is of size 3, and because these 2 match, you'll be able to get a result without any kind of error. But you can actually also perform operations if one of the dimensions is of size 1, and you'll notice that if this is 1, the other one can be like, any value, and the output you'll still get an output. Now, for example, if this 4D array instead, if this was 2, then this operation here would throw an error because these don't match, nor is one of them 1. And essentially what we did over here when we added a new axis is before we did this, where we added another dimension sort of to A, the size of A was actually just 4. It was 1-dimensional. So it's not that this value is 1, it just doesn't exist because it's 1-dimensional. So what np.newAxis did over here is it turned this array to be 2-dimensional so that this rule right over here can be checked off, where you're performing an operation where the dimensions are kind of different, but one of them is 1, so it's acceptable. Does that make sense? Sort of, kind of. Can I get a response in the chat, or just a thumbs up or thumbs down? Okay, awesome. We're not going to delve too much into broadcasting, more than that, but I'd highly encourage you to take a look at the documentation if you want to learn more. It's linked in the Collab Notebook, and it just goes into more detail of how specific cases would work with broadcasting. This example is actually the one that we just did. Okay, with that, that's all NumPy we're going to be doing for today. We're going to come back to a lot of these methods in the next 2 weeks when we're actually implementing linear regression and logistic regression. But for now, I'm going to hand it off to Nikhil to go over Pandas, which is another useful library.
All right, let me screen share and get started. All right. You guys see this? Let me know if you guys can't see it, I guess.
Oh, we can see it.
All right, awesome. So yeah, we're going to dive into pandas now, which aren't, like Vaishnavi said, they aren't actually pandas like animals, but they are pretty useful. And so basically pandas is really useful for basic visual, like looking at data like in a visual manner and like displaying it as a table mostly. It also comes with a lot of cool sorting features as well as other things that we'll go into. And in general, they're pretty similar to arrays in the way that you keep track of like panda series, or in this case. the main difference, or one of the main differences, are that we have these things called axis labels, which we'll get into. And so we can index by that instead of by integer only. And so we'll get into that, but basically Pandas is really useful for looking at your data and like analyzing it that way. And so first, let's get into actually creating a series. So a Pandas series is kind of like a NumPy array, just like you can think of it as like a row in like a table. And so here what we're doing is we're creating a Python list called list. Probably not the best practice actually. I'd avoid calling your variables by keywords, but it's okay in this case. We have another list called labels, which we'll get into. This is going to be our label, our axis labels, and so or will be. And so basically, what we're doing here is that we have another array called we're using arange for. Vaishnavi talked about it a lot, but arange is can be really useful for making a range. And what we're going to do is we're actually going to turn all of these different types of data types. So we have a list, labels, we have a NumPy array, and we also have a dictionary here. If you guys don't know what a dictionary is, it's a bunch of key value pairs. So there's a key is A, and the value associated with it is 10, and then a key B, 20, C, 30. And so all these can actually be turned into Pandas series. This is really useful because it's really easy to work with. And so let's run this. Here we go, thing. All right, and then we can run the first one. We can call our Pandas series or create a Pandas series out of our list, the first variable. And so yeah, that'll create a series. And so what it returns here is just printing out what it would look like. And so in this case, we don't have any labels added when we create it. So basically, labels just turn into indexes themselves. So it's 0, 1, 2, 3. In the next case, we actually we're gonna actually use our labels as the indexes. And so we can see here, I mean, when we run this code, what actually ends up happening is that instead of having our 0, 1, 2 indexes, we actually have an A, B, C index. And so later on, we're going to be using these labels to easily access our data. And so we can do the same for our array. Our array is a NumPy array. And so we can create a series out of a NumPy array as well. That works perfectly fine. And same for a dictionary. And so our dictionary you can think of our dictionary as like our list or our NumPy array, but with the labels already attached to them in this case. And so these are all different ways to make a series, and they're all useful depending on the context that you're in. And so it's important to know that you can make an array series in all these ways. But yeah, don't memorize these, I guess. Just know like 1 or 2 maybe, and you can always look at documentation later on. It's really important. Just look at it later. Use Stack Overflow, all those things. Like use the internet. It's a great resource. Don't memorize things. Yeah. All right, same thing for this case. This is just the reverse case actually. So we turned our list into labels, and we turned our labels into the list. So it actually isn't like, so we have up here, I'm not sure if we've gone over this yet actually in Python, but we have our keyworded arguments. So in this case, we're saying that the pandas.series method, it takes in a data parameter and an index parameter. And so in this case, we're actually specifying that the data is going to be equal to array, and the index is going to be equal to labels in this order, which is actually how it happens to occur in the code. But we don't actually have to order in this way because we have the keyword here. But in the bottom case down here, we don't actually specify data equals labels and index equals list. So we have to put it in this order, which ends up being that our labels turn into our data. So ABC is now our data in our series, and our list is now our indexes. So 10, 20, 30 are our indexes. So it's like a flipped version of all of our other ones. Yeah, hopefully that makes sense to everyone. Feel free to stop me if you have questions. Yeah, awesome. All right, so you might be wondering right now, like, why do we have these indexes? Like, what's the point of them? Like, can't we just use our index integer indexes from like positions from NumPy arrays? And so we're gonna actually use the index now and try to figure out how it could be useful. And so let's look at our series A right here. We're basically creating a series. And so as you can see from in these next two operations down here, we're creating series A, series B with different indexes. And so as you can see here, we can type in series A and kind of index it like a dictionary. So we're looking for the A index in the series A. And so as a result, because as you said here, we actually linked our A to our A index to our one data point. There's actually our linked together. And so we can access our data from our indexes. So this is really useful because it's a lot easier to know where indexes are relative to positions. Like for example, if you have like a data set of like I don't know, like pandas, about pandas, and like you have like panda weights and panda sizes, and like if you like panda weights in one column and you have like panda sizes in one column, instead of memorizing that like panda weights are column 0 and panda like height is column 1, you can just have you can have an index for that's called height and weight, and that way you don't have to memorize, oh, this is the position 0 and 1. You can just index it by that. So it's really convenient for looking at big data data and also categorized data in that case. And so yeah, we can access the E in our second series. We actually have an E index instead of an A index, and it's at the end. And so if we access E, we're accessing the last element in our series. So that's element 40. And so in this case, we're trying. So you might be wondering, can we add and subtract our pandas like we normally do with our NumPy arrays? And yes, we can. But you can see here that we don't always get the intended output. In this case, because the indexes don't line up. Because in the first index we have in series A we have indexes A through D, and in series B we have indexes B through E. We actually have one index missing from both of them, so there's one unique index in both of them. And so series A actually does not have, or series B does not have an A index. So if you add not a number to 1, you still get not a number because it doesn't work. And same thing for E. And so you can have some problems with that, which is why you want to make sure that if you want to add your series together, typically you want it so that you're making sure that the indexes are the same for everything, or for both of the series you're looking at. Cool. So that's a quick look at series. Series are kind of like, you can think of them as rows or columns, so they're like a one-dimensional thing typically. So now looking at data frames. And so data frames are kind of, you can think of them as in like, I guess an Excel sheet as a whole table. And so this is like a bunch of series together. And because you have so many series together and so many labels together, you can actually do a lot of cool things by sorting and stuff like that. So we'll get into that right now. So hidden cell. All right, so quick pop quiz. Question here is, oh, let's not show that. Question here is, we talked about this many times, but what does this line of code do? And yeah, also how, yeah, what does this NumPy array creation do here? Like what are we doing with these methods, and what does the array look like at the end? I guess, yeah, that's a good question. Feel free to drop it in chat, or what's the other option? Say it out loud. Yeah, say it out loud. It's the other option.
I think someone just added in the chat. Sorry.
Oh, yeah. Thanks for volunteering, anyways. But yeah, Elliot did say that it creates a 5x5 array with random numbers between 0 and 100. Thanks, Aryaman, for volunteering or unmuting, anyways. Appreciate it. And Elliot, thanks for the response. So yeah, it creates a 20, or to be more specific, it creates a 25, an array of size 25 of random number between 0 and 100, and then it reshapes it to 5x5. But end result is, yes, it is a 5x5 array with random numbers. And so with that array, we can create a data frame with that data. And so because we have a 2-dimensional array in this case, we can't just specify the index. We can also specify the columns. And so as you guys see here, we have our indexes, which are on the rows as we saw before. So remember back here, our indexes were also on were linked to rows. But now we have columns that are linked to columns. Yeah. That was not as inspirational as I thought it would be, but yeah, we have columns linked to columns, and so we can actually access both rows and columns, which we'll get into in a second. And so, as you guys can see here, it looks pretty cool looking at our data like this, and we can also see some trends and things that are interesting, and also we can look at certain parts of our data that are important to us. And so this is why data frames are really useful. And so, going into getting columns. You can just kind of label it, you can kind of look at it as like indexing into a dictionary. You just kind of use your brackets and put in the column name. And so in this case, we're looking at column Z. So looking back at our actual data frame, column Z is 46, 91, 36, 14, 76. And you can see that right here as well. It also adds in other information like D type. We talked about D type a bit earlier in NumPy. So type's important, as well as the name of the column as well. All right, and so we can get columns pretty easily, but we can't get rows the same way. And so if we tried doing df of a, this probably would not work. Instead, we have to do a cool method called location or lock. And so by using the lock method, we can get the values of rows or our indexes. So in this case, we're looking at the E row, and so our E series index. So this is actually 35, 73, 581, and 76. And if you don't want to use the epic power of pandas, you can use ilock to get use an integer value instead. So integer lock, but like if you're using pandas, why would you use this is the real question. So ask yourself, why would I use an integer lock when I can use an index? So yeah. And a cool distinction is that both rows and columns are series, and so you can treat them the same way. And so once you get a row and you get a series, we'll look into exactly what you can do with them soon. But just keep in mind that you can do any operation you do to a row to a series as well, or to a column as well. And so first thing you might want to do is add a new row or a new column. And so let's say we have pandas and we have a panda weights and size or heights. We want to add like panda like daily food amount. And so what we could do is we could based on our current iteration of our tables, our existing one was A, B, C, D, E, and columns V, W, X, Y, Z. And so let's say we want to add a new column. We can basically we access columns. We access columns using the syntax. We can also assign and new columns using the same thing. So in this case, we are creating a new column called new because it's new, and we're doing the same thing we did before, but a little bit different, where we're saying our data is going to be a bunch of random numbers between 0 and 100, and we need to include the indexes so that it matches up properly. And so what that does, you can see it down here if I run it again for why not. And so we can see that we actually added our a column for new, and that ends up it right here. All right, so that's adding rows and columns. Moving into getting rid of them. So let's say you want to get rid of a column because it's actually like inaccurate, like panda weights is like been messed up by some way. And so you want to get rid of the panda weights and maybe add a new one later. Or for example, you want to get rid of the new category because it's not consistent naming with the rest of your categories or columns. So you want to get rid of new. And so we have a function called drop, and kind of similar to like what you think about in, I guess if you guys know SQL at all, dropping a table is kind of similar to this, but basically drop gets rid of one of your columns. It can be a row or a column, just depending on the axis. So we have 3 parameters we've taken. That's what I started with. So first parameter is the name of the index or column. Second parameter is axis, which is you want to get rid of a row or a column. So a row would be 0, column would be 1. And in place basically means, do you want to actually modify your current data frame, or do you want to not modify your current data frame? And so on default, this is false. So typically when you drop a column or a row, you return the new data frame that has the change, but not the old one isn't changed. And so this current one is actually changing it in place. So you actually get rid of this column from our current data frame. And so if you run this here, yeah, you can see that. Look, our new column is gone after all the work we put into it. Unfortunately, it's gone just like that. So yeah, that's dropping and adding. And so with that, we can add and subtract columns and rows. So we can kind of add new data or remove data from our series and our data set. Also, we can select data based on our labels as well as our columns. And so as you can see here, what we're doing is we're actually locating using the lock function, because we're actually looking at rows, and yeah, and then so we're doing here is that we're actually locating by all the things that are both in A and V. And so what that ends up doing is basically you look at your A, you look at your V, and then you find all the intersections. So in this case, it's only one element because there's only a 43 in both the A row and the V column. And you can do this, it's not just one combination of rows and columns, you can do it for more than one row or column. And so as you guys can see here, in this example, we're looking at things that are either in B and D or X and Y. And so in this case, we got a 2 by 2, which is dependent on almost because it's, yeah, so right here. B, D, yeah, these these two and these two, yeah, cool. That had me confused for a second too. All right, so moving on. Let's say you don't want to choose something by just which index it's in or which column it's in, but you want to choose something based on like what the actual value is. So let's say we wanted to choose like all the values in this array that are equal to a certain value. And so luckily our lock function as well as our other function, our index function, are really well suited to this as well. So you can see our data frame here. It looks like that. And so what we're going to do is we're going to say, hey, data frame, give me all the elements in our data frame that are greater than 50. And so what that ends up looking like is everything that is greater than 50, you'll see the number there, and everything that's not is not a number anymore. And so basically that's your way of figuring out which elements you want. And so from here, you can select certain elements. And same thing works for, this is for general, you can actually select a certain column as well. So you can get more specific than just like the entire thing. So let's say you want to see, give me rows where all the values in W, or where values in W are greater than 50. And so here, let's look at that here. It might be easier to see here, but you can see W right here. W comma or A comma W. So our A index, our W column, this is 91. It's greater than 50. So we're going to return this row. 65 for, so the B row for W is also greater than 50. So we're going to return B as well. Our C row, which is 20, is not going to get returned because it's less than 50. 50, unfortunately, is really close, but not greater than 50. So no, D, and we're going to return E as well. So yeah, we get A, B, E. Yep. All right. And so you can get even more creative with this stuff. It's just not that, just that. And so what we can do here is that we can actually get so this is the same as our previous one. We're getting all the rows that have which have values in the W column that are greater than 50. So this stuff. And then we're grabbing the W's of those. So let's say we have In this case, we had 91, 65, and 73 as A, B, and C. And now we want to grab those actual values, the actual series itself. And so this is one way of getting all the values in W that are greater than 50. And you can get even more complicated than this. So this case is actually, so this bottom case, actually, I'll let you guys try to figure out on yourself, so on your own. So looks pretty complicated, but remember that we can think of this as separate parts. So yeah, take a minute, you guys, to look at this, this whole line and try to figure out what it might do. This might be a little bit of a hint, but it's not actually the exact same. But yeah, type in the chat or answer out loud what you guys think this might do. It's a combination of two things we've done before, but together.
The first part would just create a data frame where the values in column W are greater than 50.
Mhm.
And then the second part would get the values in column A, B, or rows A, B, and columns V and X. Oh, sorry, V and Z.
Yep, exactly. Thanks for the response. Yeah, so looking back at our actual data set and figuring out what that does, before we run this, is exactly what Arman said, is we are going to find all the rows such that their W in the element is greater than 50. So that's A, B, and E. And then we're gonna locate our A and B columns and our V and Z rows, or column, or A and B rows and its V and Z columns, and then we're gonna output that as a result. And so you guys can see here, in this case, before we run it all, we see that A, B, and E are all correct, and then we see that. So before we run right here, we get A, B, and E as our rows, and we're gonna call. We're gonna look at A and B as our rows, and we're gonna look at V and Z. So this one and this one as our column. So we're gonna look at 43, 70, and 71 are both in A and B and in V, and then 46 and 91 are in A and B and Z. And so, like we were told, it should end up with this small section. So we have a lot of freedom in how we want to select certain data, and so you can even go further than this, and there's more methods that can help you with this. But this is just a starting point, and you guys can kind of see how powerful this kind of tool can be. And so another important thing is figuring out, let's say you have your indexes, A, B, C, D, and E. And let's say you don't like them anymore. You're thinking like, oh, I don't actually like A, B, and C, and D. These are kind of not descriptive at all. And you want to get rid of them, or create new indexes, or maybe even return to integer indexes. What you can do is actually call something called reset the index. And so the method actually is called reset index with the underscore in between. And so as you guys can see, what that does is that our index actually turns into its own column called A, B, C, and D. And we actually have our new indexes are numbers. So it's like it's integer index now. And so that can help you if you don't like your current indexes, or you want to have your indexes as an element or a row or a column in your data frame, you can do this. And so let's look at how this could be useful. So right here, we have our string called new index. And so what the split method does is that it basically turns this into a list based on a certain delimiter. And so in this case, the delimiter, because there's no delimiter specified, so there's no input to this method. What it does basically, it breaks apart the string on every space and it creates a new element for each of those. So we're gonna have a list of red, comma blue, comma orange, comma green, comma yellow as our new list. That's new index. And so now we're gonna create a new index, or we're gonna create a column called new index and make it our new index list. So as you can see here, we actually add it to our list at the very end. So now we have a new a new column called new index. And so what we can do with that is actually pretty cool. We can actually set this actual row to be our new index, at least for our current iteration of our data frame. And so you guys can see here in this case, our index is still A, B, C, D, E. But after we run this, our output data frame now has an index of a new index, so red, blue, orange, green, and yellow. And so an important thing is that, like the other method for drop, you have to actually pass in the in place parameter to be true in order for this to be permanent. And so if you just leave it at that, and you look at your old data frame, it's actually going to still have your the old configuration. And so if you want to actually change this, you need to make it in place parameter true. And if you don't want to change this, you can actually like just set this equal to a variable. Like let's say you can say like you can be like I don't know, you can be like x equals this, and then look at x later on, x by itself later on, if you want to keep your data frame the same, make a new data frame. All right, and so let's look at some more practical, or a really big practical application of pandas is missing data. And so when you get complicated data sets, very often they have a lot of incomplete data. And so in this case, you can see we actually created a small data set ourselves, but the point still stands is that we have some columns in this that aren't actually numbers. So this could be like, in this case, it's actually nan, but like you could think of an example where like, let's say you're measuring pandas and you have a data frame for a bunch of pandas, like real life pandas, and you weren't able to measure the weight of one of your pandas, and so you might have not a number here or not applicable, and so we need to be able to basically deal with any of this missing data. And so a cool method to deal with this is actually called drop NA, or any basically gets rid of any rows with not any number in it. And so what this does is that now the output of this is actually going to return all the rows that have like perfectly filled in data. And so in this case, the only row that we have that has fully filled in data is row 0. And these two, row 1 and row 2, have at least one nan. So we're going to get rid of them. And so that's why it's called drop, because you're actually going to drop some arrays, or some rows, not arrays. And so again, the in place parameter exists. So in general, assume that anything that changes your array is creating a copy of it. And so if you want to make it in place, you typically use an in place parameter. So this does not actually change df. It just makes a copy of df and drops the NAs in that. And so if you want to drop columns, you can specify an axis here. So like our old stuff, axis 0 is rows, axis 1 is columns. And so in this case, only column that has full data is column C, 1, 2, 3. And so we only keep column C. But this could be a problem though. If you're going to drop all your data that has an NA in it, or a not number in it, there could be a lot of data points. So let's say you have like a huge data set of like 1,000 pandas, but you actually didn't measure like some stats in like 500 of them. You probably don't want to drop like half your data set because of that. And so what we can do instead, you can actually fill your data set to be fill all the NAs to be something that you specify. And so in this case, we're just saying fill, but maybe you want to set everything that's NA to 0, or everything's NA to the average of the data of that column, things like that. So you can deal with NAs by filling them in with using fill NA. And the same things work with fill NA here. You can specify in place as well as other things as well. And yeah, same thing applies to higher dimensional arrays. If you want to look at a higher dimensional data frame, that's what Vaishnavi said in chat. But yeah. All right. Any questions so far? It's a lot of stuff to cover. Actually, we're almost there though. So Actually, a quick reminder before we get into this is that if you're getting overwhelmed by this or feel like there's a lot of stuff to think about, there's a lot of methods in these libraries, and you don't have to know all of them. You just need to know like what you want to do for a certain set of data. And with that, you can look it up or ask somebody or look at documentation, and you could typically find out how to do that thing from someone or the internet. And so most important thing is knowing how to like set up a data frame, and as well as some simple methods so that you can get started, but afterwards you can look at other people for help or internet for help for figuring out how to do more complicated things. So don't feel the need to know everything off the bat or even know everything ever. Just know that you need to have like the general concepts in your head that are more important. All right, so group by. As the name suggests, it lets you group by things. And so it's actually a different object. So we have our data frame. And so in this case, we have data about different people on their favorite fruit and how much they ate of it. And so we're creating a data frame based on that. And so we get this data frame where you have our index, we have 6 people, favorite fruits, the person name, and number of eaten. And so what we can do is that we can actually create a group by object. And what that does is that basically it lets us group by a certain row or column. So in this case, we're going to group by the column called favorite fruit. And so if you run this, we create. It's important to note that this is actually not a data frame itself or a series. It's actually a group by object. So it has different methods, but a lot of similar methods. And so what we can do is we have a lot of options in this case. We have finding the max. So let's say we want to find the max for this row. We could just basically, I gotta take some water real quick. One sec. All right, so we have our max method right here. And so you can see it basically looks at, for our favorite fruits, we have apple, we have banana, and we have orange. So basically we're looking at each of the different ones and we're finding the maximum. So the maximum in this case would be, so we have apple from Einstein, Darwin, and Curie. And so you can see here that Curie has the most apples eaten. So she'll be the one for apple. For banana, we have Tesla and Newton. And so banana would have 6 as Newton. And the orange is just by himself as Cannon. So this would be 1. So we expect to see, oh, look at it wrong. Yeah, look at this wrong.
Someone has their hand raised.
All right. Oh, sorry, I didn't notice that. Yeah, I mean, you want to unmute?
Also ask the same question. Why is the person column just with the first people that ate a certain fruit instead of like the ones corresponding to the maximum?
Yeah, that's what I was actually confused by as well. Because I thought it should be Curie, Newton, Cannon, but it's not. Vaishnavi, Ben, do you have any idea on this? I might be misremembering this part.
Feel free to go ahead and
Okay. All right. Yeah, thanks for the question. I mean, yeah, I had the same question, honestly. I think it should be that, but I'm probably misremembering something about this method. So we'll get back to it later. Yeah, we'll come back to this soon. Sorry about that, guys, but yeah. All right, we can also look at other methods like mean. So unlike max, mean to work properly. So we're just taking the average of all the apples, the bananas, and the oranges. So there's only 1 orange, so it's just a 1 average. Bananas are 4 and 6, so it's an average of 5. And apple, same thing, but I don't want to do the math right now. So you guys can think about it. 3, I say it's pretty, 3 plus 7 plus 9 is 19. So yeah, that works out. Also some more complicated stuff as well. So standard deviation also exists. And so for things that have at least 2 data points, it works. For 1 data point, you might doesn't really work because you only have like the way the standard deviation works doesn't really apply. So you can't do that there. And then we can also look at how many times this thing occurs. And so we see that apple hasn't been eaten 3 times, banana has been eaten twice, and orange been eaten once. Actually, just pretty interesting to see that the actual columns are both the same in this case. And so you need to make sure that, or at least like typically it's best to like use a Python notebook for these types of things, because you can see the output and then based on that, determine what you want to do later. So if you didn't know what this was going to return before looking at it, you might think like the person category would still be like names. And so by looking at it like this, you realize that like actually the person and eaten categories are both changed to numbers that are the same in this case. And so you can disregard the person category in this case for looking at count. And then describe is just a bunch of different stats. And so this is just general stats. So it has a count, it has mean, standard deviation, and percentiles as well, and max and min. So it's like a box and whisker chart kind of. You can see the maxes, the mins, and the percentiles. And so far we've been looking at data that's coming from our data sets or from our lists and stuff. And so that's awesome and all, but we want to be able to like import like CSVs or different types of files so that we can get huge data sets into our programs. And luckily enough, Pandas can do that for us really easily. And so I'm not going to actually run this code for you guys right now because kind of self-explanatory, but basically you can create a data frame from a CSV, call it like using the read CSV method. And so that basically turns a CSV file that you have. So CSV, think of it as an Excel file or like a table file. Basically, it has like a bunch of columns and rows, like a pandas table or data frame. And so this turns a CSV into a data frame. You might need to have a couple other parameters here, but you can look this up yourself. And then also for output, if you want to turn your table into a CSV, so let's say you did a bunch of things on your data frame and you want to like save it somewhere as a CSV, you can do that as well with the toCSV and create a new style name. Yeah.
Really quickly, going back to our group by section. So what the max method does is for each fav fruit, it returns the max value within a given column. So of all the apple rows in our data frame, the max eaten value was 9, which is why we get 9 there. And then for person, because it's not in any particular order, it just returns the earliest index. So for apple, of all the rows that have apple as a fav fruit, the earliest one had Einstein as person, which is why. So the integrity of the rows is not maintained when you use the .max method.
Yeah, that's really cool. So yeah, so look, going back to this, like numbers are correct, but names are not necessarily correct because it's the person who showed up first. Man, I would have guessed for sure that it would be like the max of the strings or something, but that's not the case because Newton should be greater than Einstein in that case. So good to know. So there's this the strings are actually in this case are sorted by first occurrence, while the numbers are not, or numbers are like the max you'd expect. So keep that in mind. Also, another reason why you should play around with these methods on a Python notebook in general, so you can look at the output and then based on that, do further things to it, like further operations, so that you know that you're going to operate on the correct stuff. All right, and last thing before we're going to do is that, so you imported a really big data set. Let's say you imported like 1,000 pandas of data. And so it's a lot of pandas. And so what you want to do is you want to look at like what the data set looks like in a quick glance. And so what you can do is actually call a method called head. And so what this does is basically calls like the first four rows of your data frame and shows them to you. And so the reason why you want to do this instead of just calling fruits is because imagine if fruits was actually like a 1,000 row data frame. In that case, you probably won't want to look at like you probably don't want your screen to be flooded by like a 1,000 lines of just like of columns or columns and rows. And so looking at the head can give you a general taste of what your data looks like what columns you have, what columns you have, especially, as well as a general sense of like what types of data are in it. So like you can see here that like favorite fruit tends to be a bunch of strings, and favorite person tends to be unique strings, and then like eaten is a bunch of numbers or integers in this case. And so from that you can figure out a lot of interesting things about the general sense about your data set. And also if you want this in a more like, I guess, like computer version of it, a more like types and like as well as like number of columns and rows, you can call a function called info. And what info does is just gives you a bunch of the general information. It tells you what class it is. Like, so this is a data frame. It tells you how long the actual array or how many rows there are in your data frame. So in our head, we only see 4, but there's actually another one that should be down there.
Really
Yeah,
quick,
there's another one. Yeah.
Sorry, I didn't mean to cut you off. I want to correct something I said earlier. So how the dot max method operates on strings is it returns the string with the highest alphabetical value. So it just so happens that the earlier index ones had occurred later in the alphabet, which threw me off.
Yeah.
But yeah, so
Okay.
sorry about that. So dot max actually returns Einstein because Einstein occurs the latest in the alphabet when compared with the other Apple person values such as Darwin or Curie.
All right. Yeah, so okay, I was right about the string stuff. I just couldn't do string comparisons in my head. Good to know. Yeah, all right, back to info. So info just gives you general stats about the whole thing. It's kind of hard to read, but they make it a little bit bearable. They tell you how many columns and rows there are. So 6 rows, 5 columns. It gives you a general sense of like what these look like. So in this case, it shows you the index, as well as the column names, or actually this was number column names, as well as how many of these how many elements in each of these columns are not null or like not number. And so that's important for figuring out which like how many you're gonna have. Like, so from this you can figure out like if I call drop NA on my current data set, like how many rows do I expect, or how many columns do I expect to drop, for example. You can figure out by looking at this, and you can look at the type of your actual the things in your column. And so in this case, eaten is int 64, so 60, which is an type of integer, and person and favorite object or favorite fruit are strings, but pandas just looks at them as objects in this case. And so that's what it shows up as. And so it tells you a general summary of what the types are. And also a memory, in case you want to know how efficient or like how your data is currently stored. So it just gives you a general overview of like all like a bunch of stats as well as a bunch of information about your data frame. And so yeah, that's a lot of pandas. And so we looked at pandas, looked at NumPy. Together, these are really powerful libraries that can be used to like look at data, as well as select and do like basically move around data and also modify data as you please. And they're also really useful for machine learning algorithms in general, as well as visualizing them as well. And so we'll start to use them next week in our guided project. This is gonna be really fun. And so hopefully that all makes sense to you guys. And one more thing is that we actually have a worksheet. Let me show over here. We have a worksheet that you guys can do on your free time. We have like 20 minutes left. I don't know if you want to do it now, but there's a worksheet that we've created for you guys that you guys can work on if you want in your free time, that basically runs you through a couple of the things we went through today in Numpy and Pandas, and so you can get a bit more comfortable with it. And then beyond that, feel free to play around with Numpy and Pandas as well as other libraries to just have to experiment with it and create your own collabs if you want. And just like run wild with all these awesome libraries because they're really cool. And so just experiment with those. And there's also answers if you really want them, but would not recommend unless you want to get answers, which is not good. So don't get answers. All right.
You should
That's
definitely
all.
do your work though. Just try to give it a go yourself before you look at.
Oh yeah. Look at answers when you're done, I guess is a better way to frame it. But yeah, that's all we have prepared for you guys. Hope you guys enjoyed it. Please fill out the feedback form if you guys can before you guys leave. And thank you guys for coming.
And please let us know what we're doing well as what we could do better.